So, let us quickly now get back to the theory. And as I said yesterday, in evaluating the goodness of any estimator, we have to describe what is truth, we have to state the truth clearly, then only we can talk of bias, consistency and so on. So, we say here that the truth, as you have written I have written there on the screen, the truth or the data generating process is of this form. Where it is assumed that the process has the same set of regressors in your model. Now, what is Z? Of course, depends on your regressor set. This regressor set is assumed to be the same as your model, which means that in your model you have captured the right kind of regressors. If you have not, that means if there is a mismatch between the regressors that are truly generating Y and the regressors that are sitting in your model, then the excluded regressors would go and sit in Z, right. As a simple example we went through yesterday, suppose the DGP is AR2, then we know that the regressor set consists of your 2 past outputs and this is your EK, but this is provided your model is also AR2. I mean, if you are comparing with the model, suppose I have a model AR2, then the regressors are the same, right. But suppose the model is AR1, in which case the regressors in the model. So, these are the ones that are generating the series Y, or we call this as Vk here for you, whereas when you are looking at the model, particularly AR1 model, then there is only a single regressor, in which case viewed from the model what is left over is Ek minus D2 Vk minus 2. We will come to that when we discuss the example, I will talk about it. So, let us for now assume that the regressor set in your model and the regressor set in the data generating processes are identical. In practice, we would never know that. The best way to ensure that is to make sure that, in fact, you will see that least squares estimates are good so long as these errors, which are known as equation errors, are white. As long as you ensure that whatever is left over from your model is white, which is done through a residual analysis, you are safe, in the sense you can expect good estimates from your least squares method. Now, in order to discuss the properties, as I said, the foremost variable of interest is the residual, because we have just said residual analysis is the key. So, let us look at the theoretical expression here. The residual is simply Yk minus Y hat of k, there is nothing mysterious about it. We have just rewritten this residual as psi transpose k theta tilde, where theta tilde is the difference between the truth and estimate plus your equation error. So, you should observe that this epsilon k in general consists of 2 terms. In other words, even if I have included the right kind of regressors, still I cannot expect to recover the Zk, that is the true equation errors. I can never ever recover the actual errors that were generating the data for me. Epsilon, because the epsilon, the residual, contains in addition to Zk this term here, which is never going to be 0 for finite n. Now, having said that, a significant part, if you have gotten your regressors right, you should expect theta tilde, and if you have large number of observations, you should expect theta tilde to be quite small, as you will see shortly. In other words, if you have large number of observations, you would have obtained decent estimates of the parameters. Therefore, the error in the parameter estimates is going to be low, and predominantly your residuals will contain the equation errors. And that is good news, because we will see shortly that in order to estimate the variance of this part, we will use epsilon k. Why do we need the variance will become clear shortly. Now, the object of interest to us is theta tilde, because we know that for example, if I want unbiased estimates, you can define it either way, theta hat minus theta naught or theta naught minus theta hat. We want the expectation of theta tilde to be 0 if I want unbiased estimates. That is the first property of interest, if you recall from the properties of estimators. And equation 29 actually gives us the expression for theta tilde, from where we derive conditions for unbiasedness of least squares estimates. Again, you should ask yourself what is meant by unbiasedness. Unbiasedness is when you have many data records and you are estimating parameters for each of this data record, take the average of all of those estimates, you should recover the truth. If you can't, and there is a difference between the average of the estimates across records and the truth, then we say it is a biased estimate. So, you can see the expression for theta tilde is phi transpose phi inverse times phi transpose z. Clearly, the properties of theta tilde now depend on three things. One is of course the phi itself, that is your regressors, and the z, but more importantly, if you look at this expression carefully, the regressors and the equation errors appear in a particular manner, right. They, for example, here I can multiply and divide by 1 over n, so that I recognize this part here. What would be this? How can you what kind of interpretation can you attach? What is the size of phi transpose z? It is a p by 1, right. What would it contain, the p by 1 vector? So, 1 over n phi transpose z, assuming that they are all 0 mean and so on, would be the estimates of the cross covariance between the regressors and the equation errors. That is, whether there is anything common to what has been left out versus what has been included. And we will see shortly that if there is a correlation between these two, we cannot guarantee consistent estimates, or even we will also end up with efficiency and bias issues. Let us see that mathematically. So, here we have the first result, which is on the bias, and always there are two possibilities for the regressors. In the earlier example, that is the example that I demonstrated in R, what did our phi consist of? Just this morning now when we went through an example, the timestamps, simply the timestamps, there is no uncertainty about them. So, the regressors are deterministic, whereas if I look at the AR model estimation using least squares, the regressors are stochastic. So, in general you can have the regressors being deterministic or stochastic or a mix sometimes. We will not talk about the mixed case, typically that arises in system identification, but the point is your regressors can either be deterministic or stochastic. Now, if you take the deterministic case, the condition for obtaining unbiased estimates is very straightforward, because you can look at this expression and this condition. So, if I take the expectation of theta tilde, since phi is deterministic, all that is required for unbiasedness is that the equation errors that are generating this data y, they should be 0 mean, that is all. If they are not 0 mean, then it says that you will see a bias in the estimates. But that is a very mild restriction. All you have to do is make sure you include an intercept term in your model, and then the things are taken care of. That is, if you do not know a priori whether the errors in your data have 0 mean or not, all you have to do is just include an intercept term. The case is a bit more complicated for stochastic regressors. In the case of stochastic regressors, evaluating the expectation of theta tilde, that is expectation of phi transpose phi inverse phi transpose z, is not going to be easy. This is not going to be easy. When phi was deterministic, I could simply take the expectation past those regressor matrices. After all, they are all linear operations. Remember, the reason that we were able to take the expectation past these operations here for the deterministic cases, because they are all linear operations and expectation operators are linear operator. But now that phi is stochastic, I cannot really take compute the expectation so easily. So, normally what is done is we would compute what is known as a conditional bias. So, we ask for a fixed regressor set, when can I expect, that is, I keep my regressor set fixed and now I am looking at the bias. Where is the question of bias then if I am fixing the regressors? Still my z is allowed to vary, that is a random signal. So, I keep the regressor set fixed, even if it is stochastic, I will keep the regressor set fixed and let only z vary. In such cases, what is the condition on the data so that I get unbiased estimates? Now, it turns out, if you just work out the math, since we are fixing the regressors, we go back to the previous case, but the only difference is now you have phi transpose phi inverse phi transpose expectation of not unconditional expectation, but conditional expectation. And when this conditional expectation is 0, you can expect unbiased estimates. But what does conditional expectation 0 amount to? Suppose I say expectation of x given y is 0. What does it tell you about the nature of relationship between x and y? Are they independent? Uncorrelated. So, this is what I mentioned earlier. When the errors in your data and the regressors are uncorrelated, then you can expect unbiased estimates. Why am I so worried about unbiased estimates? Because I do not want a systematic error in my parameter estimate. Bias always means a systematic error. Okay? So, let me just quickly show that to you in R on the AR model part. So, let me have actually written up here a markdown document that I will upload on the website. So, let me go to the top of the document. The first thing that we will demonstrate is when that the least squares method produces unbiased estimates when there is no model misspecification. What we mean by misspecification here is the regressor set in my model and the regressor set in the process are identical. Identical meaning not value wise necessarily, but structurally they are identical. So, to do this, yesterday I said if you want to verify bias by simulations, you have to generate data repeatedly, compute parameter estimates, take the average, correct. That is what I am doing here. I am generating 200 realizations. Once I load the document, you should play around with these values. And in each realization, I have 1000 observations. And I am initializing the parameter estimate vector to some null vector. And these are the coefficients of my data generating process. I am going to generate data from an AR2 process. And I am going to repeat this how many times? 200 times. So, here is the data generating process. I am supplying the coefficients and the order. And what I am doing is I am fitting now a model of order 2, an autoregressive model of order 2 using the least squares method. In R you have AR.OLS, you have AR.Berg, and then you have AR.Euler-Walker. There are many methods for estimating AR models, of which we are interested in OLS. So, remember now look at the syntax here. I am supplying the series of length n and I am setting this AIC option to false. When I set this AIC option to true, then what this AR.OLS does is it scans through AR models of different orders up to the maximum order you specify and picks the model with the lowest AIC. But here I do not want it to do that. I know I want it to actually fit exactly the second order. Therefore, I set turn off the AIC option and set order dot max equals 2, in which case it will fit only the second order. And once I do that, I am concatenating the parameter estimates each time for each realization. So, cbind is doing that for me. That is it. And then what I have to do is I have to calculate the average of parameter estimates across realizations, right. That is what rho means is doing for me. So, let us actually run this and this chunk of code in the R markdown document and see what it has to tell me. Okay. So, first let us look at this output here. What is it giving me here? It is giving me the average of D1 hat and D2 hat across realizations. What are the true values that we have used? We have used minus 1.2 and 0.32, but remember the AR coefficients that AR.OLS returns is the negative of it, because it is looking upon as the negative sign coefficients. If you are confused, we can always in order to compare, we can always ask it to print minus of this, so that when I do this there is no confusion. It is just the difference in the syntaxes that we have been notation that we have been using. So, here you see minus 1.2 nearly and 0.32. If you increase the number of realizations, it will be more and more accurate. In this case, therefore, can I confirm that I obtain unbiased estimates? This is how you should confirm, and this is the typical way of testing for unbiasedness through simulations. Now, let us quickly move on to the case. There are other calculations that I am making, but I will not come to that now. Let us now actually generate the distribution also we will skip for now. We will check for first bias and then come back to consistency. So, what happens is, suppose I fit an AR1 model alone. When I fit an AR1 model, what is my regressor? This is a regressor. What have I left out? Ek plus D2 Vk minus 2, and what theory tells us is I will get unbiased estimates if and only, well, we have not proved the if and only if the whatever I have left out is uncorrelated with whatever I have included, and whatever I have left out is Ek plus D1 D2 minus D2 Vk minus 2. This is what I have left out, and what I have included is Vk minus 1 or minus Vk minus 1. So, this is, you can say, whatever I have left out, and this is what I have included in my regressor set. Are these two correlated? What do you think? Yes. Therefore, we should expect a biased estimate of the coefficient D1, and the question is does that happen? So, let us just run this code very quickly here, the same story except that now I am fitting an AR1 model, otherwise the rest of the settings remain the same. So, if we were to run this chunk of code here, this is the averaged across realizations. The true value is of course once again here the sign is reversed, but the true value is 1.2, whereas I obtained 0.9 That is a big difference. You can't say the difference between 0.9 and 1 point is only due to chance. Okay, maaf kar do. There is nothing like that. It is biased and theory tells you it is biased. As a simple exercise, what you should do, and you should note this down, go and generate another process, not necessarily an AR process, but some synthetic process where you generate a model data of this way, yk equals sum alpha 1 x1 square x1k plus alpha 2 x2k plus sum ek, where x1 and x2 are some random signals, they are uncorrelated. Okay. Step 1, you generate data of this form, x1 and x2 are some random signals, uncorrelated random signals, and then you fit a model. So, this would be your data generating process. Then you should fit a model including having only one regressor, throw out the x2. That means, do not include x2 in your regressor set. As a result, what would be left out is ek plus alpha 2 x2k. See if you get unbiased estimates of alpha 1. What do you expect? Yes, because x2 and x1 are uncorrelated. But that did not happen in our time series modeling, because these x2s and x1s are related, and that is why you have a problem. In this case, even though you omit this regressor, there is no issue. You will still get unbiased estimates of alpha 1. So, that is what is the meaning of that unbiased result there. You will incur a systematic error in your estimate if whatever you have left out is correlated with what you have included. How do you fix this problem in AR1? Look at residual analysis, and first you can look at residual analysis to what do we expect? We expect white residuals, or what you can do is to check if to explain why I get unbiased estimates, I can also compute cross correlation between residuals and the regressors, what I have included. But typically in time series modeling, simply looking at the residuals alone is enough. What we mean by residuals is ACF of residuals. It will tell you that the residuals are not white, and therefore you should go back and correct your model, correct. So, if I look at the ACF of here we are fitting, let us say pick any AR model here, AR mod dot resid, and you have to make sure here that the NA values. So, you can see here that the ACF of residuals shows some significant correlation. The reason for supplying this NA dot action is I have explained to you before. When you compute, yesterday we talked about this, when you set up the regressors for AR modeling, you start from 2 if it is AR2, if it is 1 you start from 1, but the residuals are calculated from 0 onwards. And it will, if you look at the first value of the residuals here, it will show you NA as the first one, because there is no prediction there. What we are telling is ACF is to ignore that NA value, that is something that you have to keep in mind. ARIMA on the other hand will not result in these things. The final thing I will just demonstrate is consistency. We will go back to the correct model and then we will continue our discussion tomorrow. It is important to understand these simulations, as important as it is to understand the theoretical results. So, you should pay attention to this. So, let us go back to the case where I correctly specify the model order, right. Then only I can talk of consistency and so on. If there is a misspecification, then there is a problem. So, here what I am showing in this chunk of code is consistency. All I am doing is I am actually generating only a single realization now. Remember, consistency looks at how the theta hats behave as you change the sample size. So, what I am doing is I am generating data of a big size, but I am only taking subsets of it. I take for example subset of sample size 10, then the next one. So, I increment here. So, you can see here the sample set is 10 power 1 and then 10 power 1.25, 10 power 1.5 up to 10 power 6, and the model remains the same. So, here is a theta hat n, this pair vec n is theta hat n, and the process is being simulated, and all I am doing is I am calculating theta hat for different sample sizes. Now, when I run this code and plot the resulting estimates as a function of n, if it is consistent, the estimate should go and converge to their true values as I increase n. So, you can see here what is happening. So, there are two plots here corresponding to two parameter estimates, right, and the blue and green lines are the true values of the parameters. One is 1.2 and minus 1.2 and other is 0.32. So, you can see that the respective parameter estimates, I do not know how well you can see on the screen, but this is the 0.32, and on the x axis we have sample size. As I increase the sample size, the parameter estimates actually go and sit at the true values, whether it is the D2 or D1. When this happens for any estimator, then you can be assured that it is giving you consistent estimates. This is what is consistency. Again, I am showing you this because sometimes it may be very difficult to understand the theory, but in simulation it is a lot more clear and obvious as to what is happening. Tomorrow what we will do is we will quickly wind up least squares, weighted least squares and nonlinear least squares, where I will talk of distributions. I will also give you theoretical expressions for what I have calculated here, and then that will be the closure of least squares.